Yeah, that'll be the plan. That assumes that we get through the content that we have expected to do before then. Colton? Yeah, it wouldn't be like the entire day as a quiz. We'd put the last 20 minutes or something to the quiz. Um, yeah, so if that's the case, you might be thinking about um, reviewing material since I don't know, reviewing material that we've covered up until now. I'm not going to say I don't know what the quiz will be on, but I'll try to find something that generally people struggled with and give you another chance at that. So, Vincent, it would likely be on Thursday, but I'm not promising the exact date. Things can get shifted around a little bit. Okay. So we are done with chapter 12, which was sources of magnetic fields. So we've learned about how currents produce magnetic fields, how moving charges produce magnetic fields. We've learned two different laws that we can use to calculate magnetic fields. The Biot-Savart law lets us calculate the magnetic field from any arbitrary shaped wire by integrating the contribution from every little chunk. The Ampere's law lets us take advantage of the symmetry property of certain problems, like a long straight wire or a circular coil of wire, to calculate the magnetic field uh, in a way that was kind of similar to the way we calculated electric field from Gauss's law. Today, we're going to look at some of the effects of magnetic fields on circuits. So we're going to start with Lenz's law, which describes how a changing magnetic flux can induce an EMF. And then Faraday's law quantifies this, so that we have some calculations we can do. And then next week, or in chapter 14, I should say, we'll start to talk about how circuit elements use some of these effects, and we'll get back to working with circuits. But before we do that, I wanted to mention that as we're going through, we have class, we have homework, we have office hours, and we have the quizzes, and they're all connected. And I wanted to just remind you of that fact, because I know it can be easy to lose sight of how these things are related. But the general process that I envision for you to do to be successful is to start by reading the content in the textbook before we cover it in class. So you should have read chapter 13, or at least the first half of chapter 13 already. And that's assigned on Canvas with the due date of that's before class. And so there's the reading quiz on that, just to check that you've done that. And then you'll attend class. Right, so in class, we'll review the main concepts from that part of the chapter. We'll do some example problems. And then after class, you've got these homework problems based on that reading. So you have a chance to do those problems yourself. And the answers are posted, so you can check if you're doing them right. Now, if you're not doing them right, the answers aren't going to help you figure out what you're doing wrong. For that, you have a couple options. You can go back and review the textbook and see if maybe some of the examples in the textbook or some description of how to do the problems helps you figure out what you're doing wrong. And you can always come to my office hours. So I have office hours on Monday and Wednesday, so between classes, basically. And I'm happy to go over problems in office hours. That's typically what I spend most of the time doing. So if you can't understand how to solve a problem, come ask me and I will explain it. Even if you can't attend office hours, you can still send it in as a question that I can do in office hours, because there's a lot of people who just join to listen in. So sometimes there's more people listening than there are questions asked. And the reason that could still be useful is because I record all the office hours. So I post them pretty much immediately afterwards. So even if you can't attend the 7 to 8 p.m. office hours, you can go back and look at the recording, which is posted by 8:30. And if you sent in a question or someone else asked the same question, you can view maybe either my explanation or my discussion with the student trying to figure out what the misconceptions were and how to solve that problem. So after you've asked in office hours or reviewed there, you can try it again and see if you can figure it out this time. So I always encourage you to do that. It's not enough just to hear someone else tell you how to do it. You actually have to go back and do it yourself. Otherwise, you're likely not digesting that until you have to apply it. So the idea is that you work on the homework problems until you get them correct, and you have the answers, so you know if they're correct or not. If you're not getting them correct and you're not doing this feedback loop, you're going to struggle on the quiz, because the quiz is based on the homework. So hopefully you've noticed that. The quiz is pretty much homework questions. I've typically tweak a variable or a question or a little bit the way it's asked, so it's not exactly the same solution, but it's the exact same method. It's pretty much the same problem. So hopefully you get that correct. And once you've worked through it, when you attend class the next day, that's often when there's group work where we discuss. If I hand out a worksheet, the worksheet is typically based on the homework that you did the previous class. So you should have already done the problems on the worksheet, basically. And it's a chance for you to try to explain to your group mates, because there's sort of 3 levels of understanding. One is like seeing it done, right? So if I do something in office hours and you watch, like, okay, you've seen it done. 2 is doing it yourself. So you have to go back and do it yourself. And then the third is if you can explain to somebody else how to do it, then you really understand. And so really the point of working in groups is to give everybody a chance to try to explain it to each other. I think that's helpful for the person explaining to really sort of organize their thoughts and make sure they understand well. And it's also helpful for other people to hear a student's perspective, because I know that like sometimes when I explain things, it might not be as clear. I'm trying to be technical and exact, and maybe you just want to hear like, okay, well, just how do I actually do this? Like, what is the shortcut? And maybe a student can help with that better than I can. So that's why we do the group work. And then at that point, hopefully you understand the content and you can demonstrate that on the quiz. Right, so it's basically you're seeing the same questions, or you should be seeing very similar questions in the homework that I go over in office hours, that we work on in the groups, and then finally that's on the quiz. Okay, so if you're skipping any of these steps, you're not as prepared for the quiz as I would like you to be. Okay, so if you can revisit this sort of flow chart and check, and just there's classes is these two steps. So while you're doing this for one set of problems, maybe that you were assigned after the Tuesday class, you're going to also have to start the same process after the Thursday class, because every class has a different set of homework. Right? So you'll always be sort of managing two sets of this workflow at the same time. Any questions about that? Hopefully you were sort of realizing most of what's here, but I just wanted to point it out in case that wasn't clear. Okay, so as I said, we're starting chapter 13 today, which is all about induction. Induction means induced, in this case, induced current in a circuit due to some magnetic field. Okay, so we're going to introduce the concept of magnetic flux. We've already dealt with electric flux, so you can probably guess what magnetic flux is, but it's really important because it's used in Faraday's law and Lenz's law, which we're going to introduce today, that describe how a magnetic field can induce a current in a circuit. So let's just see examples of this. I did this demonstration before, but here's a voltmeter, and I've got it wired in to this coil of wire, and I have a bar magnet, and let me capture this for anybody who might be homesick. Okay, so as I lower the magnet into the coil, oh, that's weird. Okay, as I lower the magnet into the coil, we see the voltmeter read some voltage. And when I pull it out, we see the same thing, although in the opposite direction. So we talked about this the last time we demonstrated that the amount of voltage we see here seems to depend on the direction that I'm moving this magnet. Whether it's in, I'm getting a positive value, and when I pull it out, I'm getting a negative value, as well as the speed. So if I do it very slowly, the effect is much less than if I do it rapidly. Okay, and so when I talked about direction, if I'm inserting this magnet one way, it's going to be the opposite as if I insert it the other way. So I just flip the magnet around, and now I'm going to see the reverse effect. Okay, so that's the interaction that we want to try to quantify today. Okay, so that's called induction. We're inducing a current in this wire that produces a voltage that we can measure, and we're using a magnetic field to do that. Okay, so these are examples that involve magnetic flux. So let's just define what magnetic flux is. we're going to use the symbol phi, just like we used phi for the electric flux. But now, just to be clear that this is a magnetic flux, we're going to use the subscript B for the flux from the B field. And if we have to go back and deal with electric flux, we'll put a subscript E on that, which we didn't need before because we only had one flux. But now that we've got two, we'll call them phi sub E and phi sub B. So this is the flux from the B field. And just like the flux from the electric field, it's going to be the dot product of the field with some area integrated over that area. So it's like the number of field lines that go through a surface that has some area. And this dot product is telling me mathematically I'm measuring like the field lines going through. So if I have a surface described by like a ring like this, and I have field lines going over it, that's not through it. And so we define an area vector, okay, for like a loop. The area vector is perpendicular to that surface, and the dot product of B dot dA, if we have a magnetic field like this, there's some angle between them that I'll call phi, and that's the value that when we multiply B times A times the cosine of the angle between them to get the dot product, that's the angle we're talking about, the angle between the area vector and the magnetic field. Now notice that's not the angle between the plane of this coil and the magnetic field, because the area vector is defined perpendicular to the plane. Okay, so that's a little bit tricky because sometimes in a problem where you have a coil of wire and you have to calculate the flux through it, you'll be given the angle of that plane relative to the field, which is not the same thing as the angle that we use here, which is the angle of the area vector. So you may have to, like, draw a picture, make sure you're labeling it and identifying the appropriate angles to use in your expression. Okay, so the reason we're going to calculate the flux is because when it changes, it's going to induce a current. And that's why we saw a voltage that depended on how fast I moved this magnet in, because that's changing the flux either rapidly or slowly. So first, let's just do an example where we calculate the flux, just to make sure we're comfortable with that. It's been a while since we had to do that. So here's a 20-turn loop of wire, right? So the wire loops around 20 times, has a given radius of 40 centimeters. It's lying flat on the table. There's a 5 Tesla magnetic field in the direction shown. That's a really strong field, by the way. What's the magnitude of the flux through the coil? So first, let's draw the area vector for our coil. It's perpendicular to the coil, so I will draw it pointing down. I could draw it pointing up if I want. I have to define a coordinate system, basically, and I'm going to define down to be my positive direction. And the reason I did that is just to make it a little easier to recognize that this angle there is the angle between the magnetic field and the area vector. And that's not the angle that we're given. We're given 25.8 degrees, but because the area vector is perpendicular to the coil and the magnetic field is measured relative to the coil, I can say that phi is 90 degrees minus 25.8 degrees. So whatever that is, 64.2 degrees. Okay, so make sure you've got your angles identified. And then we can calculate the flux. So the magnetic flux is the magnetic field dotted with the area vector. In this case, because the magnetic field is constant, this integral over the area vector, that's only really relevant when the magnetic field is changing. If it's constant, we're just integrating a constant, so it's just going to get B times the area vector. So this is just going to be B dot the entire area. Okay, so the magnitude of B is 5 Tesla. the magnitude of the area, since I know it's a 40 centimeter loop, and there's 20 turns, I'm going to do 20 turns times pi times 40 centimeters squared. That's my area. And I'm going to work this out. And I want to just go through the unit cancellation here, because on the quiz last week, a lot of people struggled converting from centimeters to meters. Not so much that I think everybody recognizes there's 100 centimeters in a meter, but when you're calculating an area where we're given a quantity in centimeters, so our area is centimeters squared, and we want to get an area in meters squared, this centimeters is being squared along with the 40. So we have to multiply by, or we have to divide by 100 centimeters per meter before we square it. Colton? Yeah, so there is an n. Yeah, let's put the n in here explicitly. Thank you. If we have a coil with multiple turns, it effectively increases the area. So we can add in the n explicitly, and that's what I've done there. Okay, so the key point is that with this is when I have to convert to meters before I square it. Or I have to convert from centimeters squared to meters squared, which is not a factor of 100, but it's a factor of 100,000. Okay, so if you write your units in with your numbers, then you can cancel your units to make sure that the units that you're getting are the units you're expecting. In this case, I'm left with a meter squared and a Tesla, so I'm going to have units of Tesla meters squared. And I worked this out. Oh, and I've got a cosine of 64.2 degrees from the dot product. And when I worked this out ahead of time, I got a value of 22 Tesla meters squared. And I can call that positive in the downward direction if that's what I've defined as positive. Okay, so flux does not have it's not a vector, but it can be positive or negative. So I've defined positive to be downwards through the loop. Any questions about how we calculated the flux? Okay, well then let's see what we can do with the flux. Faraday's law tells us that when the flux changes, okay, so this is the time rate of change of the flux, there's an induced EMF. An EMF is like a voltage. It pushes current through a circuit. So in this case, this is an EMF around the loop or around the coil that there's flux through. And it's in the opposite direction as the change in flux. We're going to talk a lot about what that means. And so basically, if we move a magnet into a coil, which is what I was doing over here, the number of field lines passing through that surface is going to be increasing as the magnet gets closer. So d phi dt is going up. There's a negative sign, which means there's a voltage that opposes that change. And that's going to actually pump current through this circuit. And in this case, resistor, I had a voltmeter that was measuring these, and I could see that. Okay, so let's talk a little bit about this sign and what that means. Lenz's law, in words, simply states that an EMF gets induced in a loop or a circuit that tries to oppose any change to the magnetic flux going through it. And mathematically, what that means is this sign is negative. Okay, but sometimes it's useful to say those words. So for example, if we have a loop of wire and a magnet here, let's say the north pole is pointing down, so the magnetic field is circulating around from the north to the south pole. If we move that magnet towards the wire, the field, or the flux, is going to be increasing. And as the flux increases, Lenz's law tells me that an EMF is induced that tries to maintain the flux the way it was. So initially here, there's no flux through the loop. So when I put flux through the loop, it's going to try to oppose that. And so if I'm adding flux pointing down through the loop, it's going to try to produce a current that opposes that by producing an upwards flux. And an upwards magnetic field tells us there must be current flowing in a particular direction by using the right-hand rule. And so that's going to be the direction that an EMF is induced that causes current to flow to offset that change that I'm introducing. Another example of this is in a generator. This is a generator. It generates electricity. This is how electricity is generated for your house, for example. Somewhere, either in a coal-fired power plant, a natural gas-fired power plant, a wind turbine, whatever it is. Most sources of electricity, photovoltaic excluded, have some mechanical energy, some turbine, that turns a coil of wire. And that coil of wire is between the poles of a magnet, so there's a strong magnetic field there. And when this coil turns, the orientation changes, and so the magnetic flux changes. Right? Initially, there's a lot of flux going through this coil, a lot of field lines pass through, but as it rotates, the number of field lines changes from being positive to negative when it rotates 180 degrees. So the flux is changing. As the flux changes, an EMF is induced that tries to maintain the flux the way it was. And that produces a current that can come out and power some circuit. Okay, so let's see this in action. You can pull out your phones, and I'm going to walk you through this demo because it's otherwise a little challenging to understand what's going on. Okay, so the splash screen explains it, but I'm here to explain it too. So you should see a magnet in front of you, horseshoe magnet, and the field, the magnetic field you can visualize with those little dotted arrows pointing from the North Pole to the South Pole. And we've got a loop drawn in the center of our screen. So right there is our loop. And you will see some yellow arrows drawn through the loop. Those represent the field lines passing through the loop at the plane of the loop. So they measure the flux. So right now I have downwards flux through my loop. So just look at mine for the moment. I'll give you time to play with your own. We see downward flux through the loop. Now, as I move my phone, I can decrease or increase the amount of flux. And when I do, the current in the loop, which we can visualize by those red charges on the loop moving. So let's see, if I increase the flux or decrease it, we see the charges spin around. They're flowing to produce their own magnetic field that's drawn as the white arrows that are going to oppose the change. Okay, so I'm going to hold this directly over the North Pole of the magnet, or I guess that's the South Pole. So there's a lot of flux pointing down. And when I move down to get even more flux pointing down, there has to be an induced field pointing up to oppose that. And that's going to result in a counterclockwise rotation of the current as seen from above. So we see that. And then when I go in the opposite direction, we see the current flow in the other way. And I can change the orientation to see the same effect, or I can do this over the North Pole and see the same thing happening in reverse. So I'll let you play with that for a couple minutes. Try to predict which way those red positive charges will flow around your loop when you move it towards or away from the pole of the magnet. You might find you need to move the phone in or out to get the ring like centered in the depth over at the same plane as the magnet. so that you can, ideally, you'd like to be able to predict the direction associated with moving the loop into or out of the magnet. So let me give you some concrete cases and ask you to work with your neighbors to try to figure out whether the current that would be induced in these black rings would be clockwise, counterclockwise, or maybe no current at all for these 6 cases. So the first case here, we have an axis right here, and our ring is going to rotate around that axis. And the magnetic field is shown coming out of the board. Okay, so initially there's some magnetic flux coming out through this ring, right, through this area. And as it rotates, that will change. Here the loop is stationary, and as it says, the magnetic field strength is increasing. Here the magnetic field strength is decreasing, and by the way, is pointed into the board. Here the loop is moving into a region of uniform magnetic field, but importantly, this region out here has no field. Likewise, the 5th case has a ring leaving a region of uniform magnetic field, going into a region of no field. And then the last one, everything is stationary. So see if you can categorize those 6 cases, and I'll number them so that you can refer to them, as clockwise, counterclockwise, or no current. You can check your work with the answers that I'm putting up. So I'm wondering, would anybody volunteer to explain number 1? You can see the answer. I think it would be useful to hear from a student's perspective rather than from me. Anybody want to volunteer to do any of these? All right, 5. Okay. Go ahead. What's 5? Why is there no current? Okay. That's right. It was Anthony? Is it? Stephen, sorry. So Stephen says the amplitude of the field is constant. And is there flux through the loop? No flux through the loop. Okay. How do we visualize flux through the loop in these diagrams? Anybody have a simple way to understand if there's flux through the loop? Bella? So the dots, it's like the number of dots. Okay, so this has a bunch of dots that represent field lines, and field lines passing through a surface is flux. So this one actually does have some flux. Is that flux changing? No, it's not. Nothing's changing. The loop is stationary, the field is constant. So although there's flux, it's not changing. So that outward flux, remember Lenz's law tells us the current in the loop tries to maintain the existing flux, but the existing flux isn't changing, so there doesn't need to be any induced current to keep that. So yeah, so that stays the same. Who would like to explain another one? Carrie? Okay, yeah, so there's flux coming out of the page, and we're told it's increasing. So Lenz's law tries to maintain the existing flux, and it has to do that by producing a magnetic field into the page to offset the increase coming out. And so if you point your thumb into the page, that's the direction of the induced magnetic field. And the current that causes it will have a direction given by the fingers on your right hand curling around clockwise, which is why we get this clockwise induced current. Yeah, Eric? All right, 3B. I didn't mean to have two threes, so I can't count. Okay. Okay, yes, that's right. So because the loop is moving into the region of the magnetic field, the number of field lines passing through it is going to be increasing, right? As we get more and more X's in this area. And so the induced field has to oppose that and point out of the page. So point your thumb out of the page. Your fingers will curl around in the direction of the current that produces that induced field. And that's counterclockwise in this example. Hidea? Okay, take us through one. Okay, yep. So our loop is rotating. So as it rotates, there's going to be fewer field lines passing through it, right? Once it's rotated 90 degrees, none of those field lines will pass through it. They'll just pass by it. So that means the flux is decreasing if we define out as positive. Um, so we need to have an induced field that points out of the page to increase, to increase the amount of flux to compensate for the decreasing number of field lines passing through. And that's going to require the current be counterclockwise. Right. So I'm repeating what you say because the recording otherwise doesn't capture that, and there's some students who'll be watching this from home. Bella? Thank you. So I'm going to use the camera on my phone here so that everybody can see the same view. There we go. I'm going to look straight down. And I'm going to put a little pad down there. And I've got a tube. This is my aluminum tube. You can see that it's got a square cross section. Where's my camera? There it is. And I can look straight down. Here's a regular non-magnetic steel ball. And let me drop it through. It kind of falls through as you'd expect. Here's the magnetic one. Let me drop it through. It took a lot longer. I thought we'd be able to see it better, but it's kind of hard. There's not much light. Let me do it again. And notice if you can watch it fall through, it doesn't stick to the wall. Okay, it falls freely, but just very, very slowly. And it's falling slowly because as it moves, the motion produces eddy currents, and those eddy currents dissipate energy as heat. And so it's taking energy away from the kinetic energy of the falling ball, so it's slowing it down. If you've ridden the drop zone at Great America, this is how you're stopped at the bottom. There are magnets on the sled, and on the rails, there's pieces of aluminum. And when those magnets pass by the aluminum, it introduces eddy currents, it stops you. It's very robust. You don't have to worry about brake pads wearing out or cables breaking. You just need to worry about physics working, and physics works. Nothing stops that. We have time for one more demonstration. So let me reposition our camera here. Okay, so for this demonstration, I've got a pendulum, a strong magnet, and an aluminum disc. Okay, so first I just want to show you that this pendulum behaves probably the way you would expect. If I swing it, it just is going to swing back and forth for some time before it eventually loses enough energy that it comes to rest. That would take a couple minutes. So here's a strong magnet. This aluminum is not magnetic. It doesn't stick to this. But when I place the magnet so that the disc has to pass between the poles of the magnet, then we can see what happens when it swings by. It stops very quickly. It's the same effect that we saw with the falling ball. So there's eddy currents being introduced that circulate around this disc, and that dissipates the energy. We can break those up if I swap this disc out for a similar sized aluminum disc that has these slots cut in it. And the effect of those slots will be to suppress or to limit the amount of eddy currents that can flow, because it's like those circular wires that are carrying the eddy currents just got cut by those slots. So let's see what effect this has with the slots. That was not what we were trying to observe. Let's try it again. I did that backwards. Got to screw it in from this side. There we go. Okay. Center it. Now there's almost no dissipation because we don't have those big eddy currents circulating. We can still have very small eddy currents circulating between the slots. But the thing is, what induces them is a change in the flux. So when the big disk passes from a region of no field to a region of field, there's a large change in the flux over most of the disk. But here, if you just look at a small segment of the disk where the currents can flow, they don't experience that change until they're right passing into the magnet. So the time over which they can dissipate energy is greatly reduced. And so we see that it has very little effect there. Okay, so we'll stop.